Hi, my name is Daniel Blackburn, and today we're going to learn about soil chemistry and how it affects plant nutrition. Alright, so this is a new lecture on the course SWAE4401, and it's about, as I told before, soil chemistry and plant nutrition. So, soil chemistry, among many other things, abundance of nutrients, for example, it's one of the growth factors for plants. It's one of the things that affect how well a plant grows in a given soil. But there is not the soil in itself is not the only factor. The availability of nutrients and water is not the only factor controlling how well a plant grows in a given soil, on a given environment. There are many others like sunlight, temperature, humidity, wind, human effects, etc. etc. But when we look at the soil as an environment, we have to think about what its main components. The pores, the air and the water, and the mineral particles. So the chemistry of the relationship between these phases of air, water, and the minerals, it's really important for plant nutrition. In the last lecture, we were talking about soil water and soil water availability to plants. Plants need to absorb quite a bit of water. The crops need quite a bit of water from the soil. And we were talking about how are what are the factors that condition the availability of water to the soil. And we saw some key concepts like field capacity and permanent wilting point, and how this field capacity and permanent wilting point varies with different textures and conditioning the amount of available water present in different soils. But today we're going to move on from those concepts, and we're going to start talking about what is the interaction between the soil solid phase, the nutrients in soil solution, and their uptake by plant roots. The plants will only uptake nutrients. There are soluble ions present on the soil solution. But the soil solid phase acts as a storage of nutrients for plants. So as the plants are depleting the solution, taking the nutrients from the solution, the solid phase, the solid particles are able to resupply these nutrients to the solution and therefore to the plants. So there is an interface between the roots and the solid phase of the soil, which is the soil solution. And this interplay occurs in a zone of soil called the rhizosphere. The rhizosphere. All right, so let's talk, before we move to talk about clays and other types of colloids, we're going to talk about organic matter. Organic matter is very complex, and it's strongly conditioning the availability of nutrients to plants. It's strongly conditioning the availability of nutrients to plants. Organic matter, we can classify them in different types of organic matter. We have fresh residue, like the rest of the crops left on the field, the litter. We have living organisms. We have decomposing organic matter, which is in some state of decomposition. And we have stabilized organic matter in soil, also known as humus. Some of this humus is stabilized through their interaction with other colloids like clays in the soil, or iron and aluminum oxides in acid soils, for example. But we are interested in two things, in many things actually, but in which ways these organic matter are affecting plants, in which ways the organic matter can help plants in soils. And actually there are three different ways this organic matter is helping plants. One is the most obvious one. It's being decomposed, and as it is being decomposed, provides nutrients to plants. So in the chemical way. But it's not the only chemical way organic matter is affecting soils. It's also changing the behavior of other colloids in the soil. It's regulating pH. It's improving the cation exchange capacity. We're going to talk about this concept in a bit. And in physical ways, it increases the structure of the soil, water retention, and infiltration rates, and thermal properties of the soil. But the more important also than this, not more important, but as equally as important, is that organic matter is food for the microbes. It's food for the microbes. The majority of the soil community, the microbial community, they are heterotrophs. It means they're using organic matter as a source of carbon, as a source of energy. So these microbes are really important for plant nutrition in many ways, fixing nitrogen, solubilizing phosphorus, and acting in many ways protecting the plants from pathogens. There are many roles of soil microbes in soils. And without organic matter, this activity, the activity of the soil microbes is decreased strongly. Yes, strongly. So these are the three main ways in which organic matter is playing a role in plant nutrition. Yeah? So organic matter can be a source of nutrients by itself, by being decomposed by microbes. So how do microbes decompose organic matter? By releasing enzymes into the soil. Yeah, hydrolases that break down the bonds between carbon molecules, carbon to carbon, carbon to nitrogen, carbon to phosphorus, releasing these nutrients into the soil solution and making these nutrients available to plants. So carbon in itself is not from the organic matter, is not a source of carbon for plants because plants photosynthesize, but it's a source of carbon for microbes, and by doing that, it becomes a source of other minerals for plants. Now, talking about the soil particles, excluding organic matter, the soil solid phase, we can classify this in clay, silt, or sand. You remember this from Introduction to Soil and Water. And this classification is based on the size. Different agencies or countries will have different definition of those size, especially when it comes to the silt and clay sizes. But in general, you would say it's just sand is a very raised that you can feel it on the touch. The silt, it feels very smooth on the hand, but not sticky. And the clays will be the very sticky substances on the soil. Yeah, so they're classified by size, but you can also classify them by how you feel them in general. Why we are talking about this? We are interested in clays. Yeah, we're very interested in clays. Clays are heavily conditioning the chemistry of nutrients in soils because clays, along with humus, they're colloids. Yeah? They're colloids. And what are colloids? They're very extremely small particles that cannot be seen even with the light microscope. They need an atomic absorption microscope. They have because they are small, they have a very high surface area, and they have charge. Yeah, the main thing about these colloids is they carry charge, and this charge needs to be compensated in the soil solution by ions, and therefore the ions that stick to these colloids, they are adsorbed into the colloids, and this soil, because of the charge of the colloids, it acts as a reservoir of nutrients. Yeah? If you have charge on the solid phase, you need to compensate that charge with ions, and those ions are the nutrients for plants. Yeah? The nutrients for plants are ions that can be stored, adsorbed on the solid phase. This is just explaining really quick, reminding you the concept of surface area. And that large particles will have less surface area than small particles, and because if you think about how you split them, it will show more faces of these particles, and therefore it will have more exposed area. So the reaction between the solid phase and the solution phase, and the soil water, the nutrients are interchanged between the solid phase and the solution through those surfaces. The more surface area that you have, the more reaction you will have, the more the capacity of the soils of storing nutrients. Yeah? The amount of surface area is directly proportional to the capacity of the soils of providing nutrients for plants. And the charges that you have on these clay particles, they are divided in two different types of charges. One is permanent charge, and the other one is pH-dependent charge. The permanent charge does not change when you change the pH of the soil solution. If you change the pH of the soil solution, there's no change on the permanent charge. The reason for that is that the permanent charge is originated inside the structure of the clay by a process that is called isomorphous substitution. Yeah? The process called isomorphous substitution. Whereas the pH-dependent charge, it's a charge that is generated on the surface of the clay. And therefore you can protonate and deprotonate those oxygens on the surface of the structure, and by doing that you can change the amount of charge that you have. We're going to explain that in a bit. The isomorphous substitution is when you, in the original structure from the clay, you have some ion of higher valence, and this ion of like aluminum, for example, or silica. Silica can be substituted by aluminum, and therefore you lack one charge, and it becomes negatively charged. So the isomorphous substitution, it's originated inside the structure and therefore cannot be compensated by covalent bonds to that structure. So the covalent bonds will make a stable bond, whereas if you have the isomorphous substitution, it can only interact with ions by electrostatic interaction, not by covalent bonds, and therefore these ions can easily absorb and desorb from the solid phase. So just a clarification, adsorption is when it sticks to the solid phase, desorption is when it's released from the solid phase. Yeah? So this isomorphous substitution is generating permanent charge on the soil, the charges that are independent of pH. Whereas the pH-dependent charge, they're formed on the surface of these clays, and on the clays, they're more present on the edges, and organic matter all over the organic matter, and the iron and aluminum oxides all over them, but on the clays, on the edges of the lattices of the clays. How it works for the pH-dependent charge is, when you have low pH, you have a high concentration of protons on the solution. Those protons will stick to the hydroxyl, and by protonating the structure, you create a positive charge. If you start rising the pH, you reach a point where these protons are released back into the solution, and this point is called the isoelectric point, or the 0 point charge of the clay. Yeah? If it's a pH-dependent charge clay, you will have that at some point you have a net charge is 0. The net charge 0 is the isoelectric point, or the 0 point charge of this clay. If you continue increasing this pH, the concentration of hydrogen in solution becomes so low that even it will lose those protons and generate negative charge. Yeah? So normally the 0 point charge is on the acid range. So most of the soils will have negative charge as pH dependent. But how many negative charge, the amount of negative charge by pH dependent charge is regulated by the pH of the solution. So the more you increase the pH, you increase also the amount of negative charge as pH-dependent charge. So this is only review from soil introduction to soil and soil chemistry. These concepts are already given before, but it's worth reminding why we care about this in the context of plant nutrition. Yeah? It's about the nutrient interchange between the surface of these clays and the solution and with the plants. And here it goes. Yeah, these different clays will have different properties. Different clays will have, including the humus, they will have different amount of charge, and you will have different types of charge. Yeah. Different surface areas, so all this will condition how much ions you can absorb. So the highest amount of charge per gram of material is on humus. Yeah? After that, you have the 2-to-1 clays being more charged, and then after that you have the 1-to-1 clays. And of course, the nutrients that plants use, they are ions. Yeah, they are ionic nutrients, either cations or anions. But these ions interact with the solid phase. If they are positively charged, they will be attracted to the surfaces, and if they are negatively charged, they can be bridged into these surfaces by another cation. Yeah, so if you have, for example, calcium can interact with the phosphate and with the surface of a clay at the same time, bridging those anions so they can absorb to the solid phase. So both cations and anions will interact with the solid phase. Some ions will interact more strongly than others, and this will regulate also their behavior in soil. How mobile are they in soil depends on how strong the interaction is between these ions and the solid phase. So here is an exemplification of the adsorption process, and then you have a phosphate molecule which is forming here inner sphere complex adsorption. Yeah, the inner sphere complex is when it binds covalently to the surface of this colloid, and here this phosphate here is diffused or not adsorbed at all. Yeah? But you can form hydrogen bonds and have an electrostatic interaction between different ions, hydrated ions, and the surfaces of these clays or colloids in the soil. The strength and the behavior of this interaction between the solid phase is measured by the adsorption isotherms. Yeah? Adsorption isotherms. Here are some examples of adsorption isotherms. On the y-axis, you will have the amount of adsorbed ion, and in the x-axis, you will have the amount of the ion on the solution. The more ion on the solution, the more you will have on the solid phase. But it reaches a point that the solution concentration is so high that the solid phase becomes saturated. So this becomes flat. The closer this curve is to the y-axis, the higher the affinity of the ion for the solid phase. The lower this curve is, the closer it is for the x-axis, the lower the affinity. Yeah? The lower the affinity for the solid phase. So we are talking about how strongly, with how much energy, an ion interacts with the colloid in the soil. So we have the colloids regulating how much charge you have, but the ions also compete with themselves, with each other, for these adsorption sites on the soil. They have competitive adsorption. Some are more attracted to the colloids than other ions. And if we compare how attracted these ions are to the solid phase, we can form an order of energy in which these ions are interacting with the solid phase. And the order of this energy of interaction is called the lyotropic series. Yeah? The lyotropic series organizes these cations in order of strength of interaction with the solid phase. So hydrogen is the one with highest affinity for clays and iron oxides, aluminum oxides, and organic matter. Whereas sodium is the one that has lower affinity. So you will find sodium and potassium most likely in solution, whereas you will find calcium, aluminum, and hydrogen most likely associated with the solid phase. So they're less mobile if they have higher affinity. They're more mobile if they have lower affinity. And if you have more, this is absorption is a function of both this affinity but also the concentration. If you have too much of an ion, even if it has low affinity, it will be able to displace other ions from the solid phase. So these two things are important in adsorption. One is the affinity, exchange affinity, and the other one is the concentration of these ions. Why now? Why one ion will have more affinity than another one? The reason is what we call the charge density. Yeah, if you imagine a hydrogen has only one valence, one plus, but it's very small. Yeah, in the same position when you have one sodium, you can fit many hydrogen. So in the same space, the density of the charge will be very high. So this charge density of these ions also it's what regulates this exchange affinity. Yeah? The smaller they are for the same valence, the highest affinity. The bigger they are for the same valence, the lower the affinity. So we come to this concept that the solid phase of the soil by itself, all the colloids add together, if you sum up all the charge that the soil possesses, all the charges together of the soil, they account for the cation exchange capacity. Yeah? The cation exchange capacity, it's the number of charges. It's equivalent to how much charge you have on the soil. Yeah? It's not, you measure them by adding up the ions, but it's not a sum of the ions, it's amount of the charge that the soil possesses. This is a measurement of the capacity of the soil to retain nutrients. The highest the cation exchange capacity, the highest the capacity to retain nutrients. You can have some calculations about cation exchange capacity, but we will not worry about that at the moment. The next concept is base saturation. Yeah, you have two types of ions. Yeah, on the soil you have bases and you have acid cations. Yeah, you have hydrogen, aluminum, and iron. They are acid cations, whereas all the other cations, they are bases. Why do we classify it like that, as bases or acid cations? Is because the reaction they have. When they leave the solid phase, do they increase the pH or do they decrease the pH? Yeah, this is the concept that we have. If they increase the pH, we call them bases. If they decrease the pH, we call them acid cations. Okay, so if you release a proton by itself, it's already decreasing the pH. Okay. And aluminium also, because the aluminium forms hydroxides, and iron also forms hydroxides on the soil. It will also cause the same effect. Yeah, if you release that into solution, you will take some hydroxyls, and by taking some hydroxyls, you will increase the concentration of H+. But that is for another lecture. Yeah. pH by itself, it's very important for plant nutrition. Yeah? Base saturation is how much of this cation exchange capacity is occupied by bases. Yeah? But the bases and the protons in the system, they have an effect by itself on plant nutrition. Yeah? So pH What is pH? Just reminding you again, pH is the concentration of H plus in any solution. Yeah? pH is the concentration of hydrogen. And why do we care about pH? The water by itself dissociates and H plus and OH. In pure water will have a concentration of 1 times 10 to the minus 7 hydrogen free on the solution, free on the water. Pure water at pH 7, neutral conditions, will have a concentration of 10 to the minus 7 moles per liter of hydrogen. So this is neutral condition. If you increase the amount of protons, you decrease the pH. If you decrease the concentration of protons, then you increase the pH. So it's a log scale. It's an inverse log scale. Yeah. How does it work, the inverse log scale? It means that if you change 1 point pH, you increase 10 times the concentration of hydrogen. Between 7 and 6, there is 10 times more hydrogen at 6 than there is at pH 7. And if between 7 and 8, there is 10 times more at 7 than there is at 8. So, and it's always working, it's a negative of the logarithm of the concentration of hydrogen. So it works in an inverse manner. Yeah? So pH controls a lot of things in soil. We already seen that pH is controlling the pH-dependent charges. Some charges of the soil are increasing or decreasing based on the pH of the soil solution. But it's highly regulating the experience of the plant of the soil. The plants will have to deal with the acidity of the soil can hurt the plant through the release of toxic ions like aluminium, for example. Aluminium will be very toxic to plant roots, and it only occurs when you have very acid pH. So when you have very acid pHs, you will need to regulate this pH up, and when you have very alkaline pH, you need to regulate that pH down. And the main reason for this is that the solubility of ions on the soil will be regulated by this pH. The ions can precipitate or be soluble, and this solubility it's a pH-dependent solubility. Okay. Let me try to show here. This is the figure explaining this solubility of different ions in soil solution at varying pH. And you will see that near neutral condition, at acidic condition, is where we have that most nutrients are soluble. So this is the best range of pHs for plant, which should always search that the soil pH will be somewhat near acidic neutral conditions. Yeah, neutral conditions. Next thing I want to talk about is the concept of reserve acidity and reserve basicity. The soil acts as a storage of nutrients, but also acts as a storage of hydrogen. The hydrogen is the ion that possesses the highest affinity with the solid phase. So think about the soil as this reservoir on the left, and think about the soil solution as the reservoir here on the right. If you have a high cation exchange capacity, you have a big reservoir on the solid phase of the soil. If you have a low cation exchange capacity, you have a small reservoir here. What happens when the plant takes nutrients from the soil, or when you wash the soil and remove some ions? You are only removing from the soil solution here on the right, yeah. And this is what happens. When you remove ions from the soil by washing or by absorption by plants, you're removing from the soil solution. And what happens is the solid phase will replenish the solution, will supply the solution to its previous level. But of course, as it resupplies the solution, it's also depleted. If you have a high cation exchange capacity soil, the depletion of the solid phase is small. But if you have a low cation exchange capacity, like sandy soils, for example, the depletion of soil solution is much higher. So this is the concept of reserve acidity and reserve basicity, but also it serves as an example for you to think about how the soil acts as a reservoir of nutrients for the plants. Yeah? So precipitation and dissolution of ions is really important in the soils, and this precipitation is highly dependent on pH. So here is an example is about phosphorus. Phosphorus is available to plants as phosphate ions, and in acid soils, these phosphate ions will be precipitated with iron and aluminium. Yeah? But when you have in alkaline soils, these phosphate will be precipitated with calcium and magnesium. And here are a range of calcium phosphate molecules that will have a decrease in availability to plants. So monocalcium phosphate will be more available, and carbonate apatite will be highly unavailable to plants. So what we want is keep the soil at the pH range where you have highest solubility of these ions for the plants. When we think this interaction between the plant, the solid phase, and the soil solution, we have to think about this is not a passive interaction. Yeah? This is a rhizosphere system. It's a disturbed system. And how is this rhizosphere disturbed? The plants are taking the nutrients from the soil solution. As they take the nutrients from the soil solution, there is diffusion through the soil solution. Yeah? There is desorption from the solid phase. There is mineralization from the organic matter. And we have in between the roots in the solid phase a whole community of microbes that will affect both the plant roots and will affect the interaction between the nutrients in the solid phase in this system. So microbes will be negotiating the availability of the nutrients for the plant roots in the system. And the plant roots are trying to condition and regulate the solution in many different ways. There's strategies of the plants for dealing and regulating this soil solution. So one of the big strategies of the plant is pH change. Changing the pH of soil solution will change the solubility of ions. Yeah? But also it releases carbon molecules into the soil as organic acids, for example, and then to feed the microbes. And by feeding the microbes, you create this cooperation. It's called protocooperation. The microbes want the plants to be healthy, so the plants will provide these carbon molecules for the microbes. And by feeding the plants with nutrients from the soil, the microbes help the plants to grow, and then therefore they also benefit by receiving these sugars and organic acids from the plants. Those carbohydrates serve as foods for the microbes. The plants and the microbes themselves, they are releasing enzymes into the systems, siderophores and surfactants. Yeah? Siderophores and surfactants, they are acting and solubilizing these ions on the soil. This microbial biomass, it's composed by a big range of microbes, but the most active groups are bacteria and mycorrhiza. And we have, of course, the mesofauna in the system, which are grazing these microbes and cycling the nutrients on the system. So it's a very complex environment. And this complex environment, which has the chemistry between the solid phase and the solution phase, the interaction between the root and the solution, the microbes in the middle of all of this. So there's chemistry of sorption, desorption, chemical properties of the soil. There is the properties of the plants and the ability of the plants of influencing the soil properties. or trying to extract these nutrients from the soil. And you have the microbes that are also interfering on this. So all this complexity is what we call the rhizosphere effect. Yeah, it's not straightforward chemistry or straightforward chemical reactions or biology in the system, or it's not a straightforward physiological trait of the plant. It's a combination of all of those. Yeah, a combination of all of those. And this is the exemplification of this combination. You have all the properties of the soil, but also the factors related to the plants and the microbes that are regulating the bioavailability of nutrients from the plants. So we have clay content, organic matter content, oxide content, concentration of the nutrients in the soils. We have microbial factors and the roles of microbes, the function of different microbes. We have roots exudating many different things into the soil solution. We have properties such as redox potential, salinity, and pH, also being very key on the availability of these nutrients. So this is the lecture about the chemical properties of the soil and how it's affecting the nutrition of plants. I hope you enjoyed, and I see you in the next lecture.